好的，大家下午好，我们现在就要开始我们今天精实又精彩的下午场研讨会。那我们早上是讨论台湾的现况，下午场呢则是由丹麦专家来跟各位分享，然后之后会有台丹的座谈。首先，我们就邀请丹麦沼气协会营运长 Bruno Sander Nielsen 跟台湾的朋友们分享丹麦沼气的发展状况，以及丹麦沼气对净零的影响。那 Bruno 他自己本身在丹麦农业与食品产业协会工作超过20几年，所以他自己本身参与也见证了丹麦农业绿色转型的历程。那现在就请 Bruno 为我们跟大家做简报。Good morning, Bruno. 然后跟大家说一下，丹麦目前的时间是早上。
Good morning. Can you hear me?
Yes, we can hear you.
Okay. Good morning. Thank you for the invitation to talk at this seminar. It's still very early in the morning here in Denmark. I hope you have had an interesting seminar until now. Next slide, please. The Danish Biogas Association is the organization for all the stakeholders in the biogas sector in Denmark. It's the owners of the biogas plants, the producers of biogas, and the suppliers of biomass from agriculture and industry, and also the farmers who use the digestate as a fertilizer. We also have the technology and equipment suppliers and the consultants and the knowledge institutions as members. So the members are the representatives from the energy sector, the waste handling sector, and the agricultural sector. The mission of the organization, in which I have been working for more than 25 years, is to promote the production and the use of biogas and to promote the circular economy, the reuse of organic residues to produce renewable energy, and to recirculate and reuse the nutrients from the residues from agriculture, households, and industry. And we focus very much on capacity building, networking, and knowledge sharing in the sector. Next slide, please. On the left-hand side, you can see the development in the biogas production in the recent 25 years in Denmark. We had a steady or slow increase for many years, but after 2012, we have seen a very rapid development. This is due to the adoption in the Danish Parliament of new framework conditions, which improved the feed-in tariffs for the electricity production and introduced new feed-in tariffs for injection of the biogas into the gas grid. The increased production is in the agricultural-based biogas plants. You can see this is the green ones, where we co-digest livestock manure with organic residues from agriculture, from industry, and from households. On the right-hand side, you can see the relative origin of the biogas production. 25 years ago, 60% of the biogas was produced in wastewater treatment plants in the municipalities and was collected from landfills, and only 40% was from agricultural-based biogas plants. Now, more than 95% of the biogas is produced in the agricultural-based biogas plants. So the Danish biogas sector is agricultural-based, and in 2020, we digested 20% of the Danish livestock manure in biogas plants, and we produced 20 petajoules of biogas, which substituted 20% of the natural gas consumption. Next slide, please. Next slide, please. Next. Yeah, thank you. This slide illustrates, and you can click next 3 times also. Thank you. This slide shows the Danish biogas model. The main biomass input is livestock manure, both liquid slurry and deep litter. This is mixed in with organic residues from agriculture, from households. Can you come back to the presentation mode? This is mixed with agricultural residues from agriculture households industry and the service sectors. And the main output is the digestate in the bottom left, which is used as a fertilizer in agriculture. This ensures, that the nutrients, the nitrogen and the phosphorus and the potassium is recirculated and used as fertilizers for the crops, substituting chemical fertilizers. In addition, the value of the livestock manure as a fertilizer is improved. This increases the yield and reduces the risk of leaching of nitrates to the aquatic environment. So the biogas plants are actually a fertilizer factory, and in addition, we produce the biogas, which is a renewable energy source that is very valuable, mainly to ensure that those sectors where electrification is not possible can stop using fossil fuels, mainly in the heavy-duty transportation and in the energy-intensive industry. And we can ensure the electricity supply when windmills and solar panels can't meet the demand. All this is in the Danish biogas model based on utilizing residues, turning them into valuable fertilizers and renewable energy. Next slide, please. This slide shows that the biogas plants are distributed all over Denmark. Wastewater treatment plants in all major cities and have biogas plants to treat the sewage sludge before it is used as fertilizer in agriculture. The agricultural-based biogas plants, the green ones in the map, are mainly in the western part of Denmark. That's where we have the intensive livestock production. On the left-hand side, you can see a number of Danish agricultural-based biogas plants. Upper left, a cooperatively owned biogas plant started in 1997 by 17 farmers in New Zealand. Upper right, a farm-scale biogas plant established on a pig farm in 2002, owned by a farmer. Lower left, a plant from 1990 in the southern part of Denmark, owned by more than 60 farmers in a cooperative. And the lower right, a plant from 2016, owned in a 50-50 ownership by a German energy company and the local farmers. Next slide, please. And you can push 10 times here. Sorry for the animations. Originally, we only had the main issue when it comes to biogas is the support mechanisms. Until 2012, we only had feed-in tariffs for electricity production. In the 2012 energy agreement, the Danish parliament increased the feed-in tariffs for electricity production and introduced several new feed-in tariffs. Upgrading and injection into the gas grid is by far the most important, but we also got support schemes for the direct use of biogas in industry, for transportation and in heat production. Next slide, please. You can see on the left side, the increase in the biogas production has almost entirely been in upgraded biogas injected into the gas grid. The green one is the use for electricity production, and this has been constant during the recent years. As shown in the middle figure, all the biogas was used for the combined heat and power production until 2013. Last year, however, more than 70% of the biogas was injected into the gas grid. This is very important as we, in this way, can turn biogas into a storable renewable energy source. We can inject the biogas into the gas grid and keep it there for either a few hours or many months, and we can redistribute the biogas through the gas grid from one end of the country to the other. And we can store huge quantities of energy in the Danish gas grid. If we calculated this in electricity, and we actually could charge the batteries in millions of Teslas electrical vehicles. If these vehicles were placed on a parking lot, this parking lot will go 13 times around the globe. So it's huge quantities of energy we can store in the Danish gas grid, and this is very important. Next slide, please. And the Danish Energy Agency, the government, has predicted that the future development. The left-hand figure shows the authorities believe that the biogas production will be more than doubled within the next decade. The same development is shown as the green part of the right-hand side figure. And you can see it's still the expectation that it will be biogas going into the biogas grid. As the total natural gas consumption will decrease, the share of the gas the share of the gas consumption that will be biogas will increase to at least 70% in 2030. So we will go from a full use of fossil fuels 7 years ago, and by 2030, 70% of the Danish gas consumption will be biogas. Next slide, please. I'm sorry, this slide is a bit complicated. The left-hand figure shows the total inland biomass resources that can be utilized in Danish biogas plants, more than 20 petajoules. And the slide actually shows a gradual increase through the years in the utilization of livestock manure, the brown parts of it, the industrial residues, the blue ones, the food waste, the red one, agricultural residues, the green one, and straw, which is the yellow ones. On the right-hand side, you can see the demand for biogas from different sectors as it was expressed in the climate partnership reports. All the industrial sectors was asked by the government to make last year as a roadmap to ensure that each sector will meet the Danish ambition of a 70% reduction in the greenhouse gases by 2030. And as you can see, the increased production of biogas can meet the demand. Next slide, please. The Danish biogas production is, as I said, based on residues. The left-hand figure shows the proportion of different sources in tons input, and the right-hand side, the origin of the biogas. This was in the year 2019 to 2020, from summer to summer. Livestock manure is almost 80% of the input, and it makes up 1/3 of the biogas production. Industrial residues was 12% of the input, the blue ones, and almost 1/3 of the output. And you can see the red ones is energy crops. We are at a very low level, only 4% of the input and 10% of the output. So again, the production is based on residues and mainly on inland residues. Next slide, please. Again, a bit slightly complicated figure, but it only shows on the left-hand side, on the right-hand side, on the left-hand side, the production of biogas increasing from a little more than 20 petajoules right now and into more than 50 petajoules in 2030. And we have drawn backwards from this expectation of the Energy Agency in the energy production into which biomasses will be used in the biogas plants. And you can see again the main input is livestock manure, the brown ones, but you can also see that the biomass which will increase in utilization is straw from the cereal production, the yellow ones, and especially the straw will make up quite a proportion of the produced biogas when we come to 2030. On the other hand, the blue one, the use of industrial waste, we expect will be rather constant. But at the right-hand side, you can see still livestock manure is in tons by far the most important feedstock. Next slide, please. And here you can see the expected share of the use of straw and livestock manure. And as you can see, we will at least end up using 60 to 70% of the livestock manure in 2030. and straw, where we will use at least 30% and perhaps 40% if we were a bit more ambitious in the development, not only going for a 70% share of biogas in the energy consumption, but 100% biogas in the gas grid. That's the green lines. But you can see at least 60% of the livestock manure will go to biogas plants, and more than 1/3 of the straw will be used in biogas plants by 2030. Next slide, please. What is the impact when it comes to climate change? The use of livestock manure and biogas plants is a very efficient way to reduce the emission of greenhouse gases. In the biogas plants, we collect the methane that is emitted from the storage tanks with livestock manure, and afterwards the produced methane substitutes natural gas. In this way, we have a double climate effect. We reduce the methane emission from agriculture and the CO2 emission from the energy sector. And you can see on the left-hand side that it's most efficient in the energy sector, and the blue one is the reduced methane in agriculture from this year until 2030. And as shown on the right-hand side, we can actually increase the positive effect in agriculture if we make sure that livestock manure is transferred to the biogas plants within a week, compared to the normal procedure in Danish farms where the pig slurry can stay in the stables for 3 to 4 weeks. Normal is the climate efficiency in reduced emissions of greenhouse gases when the livestock manure is 3 to 4 weeks when it goes into the biogas plants. And if we could get it more frequently, every week, we could add the dark green on top of it. Next slide, please. At the same time, we can utilize the energy potential of the straw without depleting the soil carbon content as shown on the left-hand side. The blue line shows the carbon incorporation into the soil if the straw is directly incorporated into the soil. If the straw was used in biogas plant, we digest a little more than half of the carbon content, but the carbon left in the digestate will stay in the soil as humus, and in the long term run, the soil carbon content will be at the same level as if the straw had been incorporated directly. So we can utilize the straw for energy purposes without depleting the soil carbon content. And on the right-hand side, you can see that the anaerobic digestion in the biogas plants also reduces the bad smell we all know from fields where livestock manure has been used as a fertilizer. The reduced smell is partly due to the degradation of the smelling agent and partly due to the fact that the manure is turned into a thinner liquid that disperses quickly into the soil. So we reduce the bad smell of the livestock manure. Next slide, please. We also in the biogas sector is labor intensive, both direct jobs on the biogas plants, the green ones, but mainly from the continuous maintenance of the biogas plants. That's the red one. And of course, there's also a lot of jobs in the construction phase, the blue one. So we keep jobs in the agricultural sector, but also in the service sector. Next slide, please. When it comes to the legislation, the digested biomass is actually regulated as livestock manure. And the acceptance of the digestate as a fertilizer among the farmers is very important. Here, the Danish legislation has been very important. First and foremost, by setting up quality criteria that has to be met for all the waste streams other than livestock manure regarding the content of heavy metals and other hazardous substances. But also by stating that the digestate has a status of being livestock manure if more than 75% on dry matter basis of the input is livestock manure. This means that the farmers are not using waste as a fertilizer, but they use livestock manure co-digested with safe organic residues. In addition, the animal byproducts regulation in the European Union set up tough standards to ensure there's no risk of spreading pathogens and diseases. Next slide, please. This slide is again a bit complicated, but you can recognize the green as the increased biogas production through the last 30 years. The red bars are the feed-in tariffs for the produced electricity. And you can see the biogas production increase came when the feed-in tariffs were high enough to make the projects bankable. The level of the feed-in tariffs in the recent years are, as far as I know, quite close to the current feed-in tariffs in Taiwan. The development in the early years, next slide please, was not the economy of the plant, but the legislation saying that the farmers from the late 80s had to invest in storage capacity for livestock manure. One backwards, please. Yes, thank you. The farmers in the 80s had to invest in storage capacity for livestock manure, and there came restrictions on the volume they could spread per hectare. Here, the centralized biogas plants were an excellent solution as they can redistribute manure from pig or cattle farmers to the plant producers. But the feed-in tariffs were not the only important incentives. Investment subsidies, both in the early years of the development and in the years after the financial crisis, were very important. But the combination of these with legislative push and economic pull that pushed forward, it was the combination of these legislative push and economic pull that pushed the development forward. Next slide, please. So to conclude, the biogas plants are very efficient to solve multiple challenges to reduce the leaching of nitrates, ensure the recirculation and the reuse of nutrients from food waste and residues from food industry and so on. And we can reduce the greenhouse gas emissions from agriculture and from the energy sectors by substituting fossil fuels, and we create jobs both on the biogas plants and in the maintenance and in agriculture. Next slide. Next slide. Thank you, and we'll take the last slide at the panel discussion. Thank you for the attention.
Thank you, Bruno. 谢谢丹麦沼气协会营运长 Bruno 的简报。然后他等一下也会参加下午等一下的座谈。